because when he was still an undergraduate student, he joined my group. And from that time on, he got into his master's and then PhD. He's a chemical engineer by training, but got his master's and PhD in metallurgical engineering, mineral processing. And in 2014, he was awarded a couple of international awards, which is the Young Researcher Award from MEI, and then also the Young Author Award in the IMPC. And Rodrigo now has been faculty for over 10 years at the University of Rio de Janeiro, with me here in the Laboratory of Immunotechnology, LTM. And he's been really actively working on modeling of a number of systems, including comminution systems, in particular advanced comminution models, but also has been really keen on developing a better understanding of handling of materials, especially sticky materials. And so really widened quite a lot his background. He's supervised a number of master's students and PhDs, very active here in Brazil. And I think since last year, he became a GCC member. So we're looking forward to see his presentation. And I think, please, Rodrigo, go ahead to talk about dynamic simulation.
Okay. Thanks, Marcelo, for the nice introduction. So good morning, good afternoon, evening, everyone. So the topic of my talk is just a second here. Okay. Model and simulation of comminution circuits using Dyssol. It's a topic that we recently went back the last 4 years at least. The idea here is to give you a brief introduction on modeling and simulation of comminution circuits, and show you some case studies and talk about the GCC Dyssol project, which some of you may already know, but also to introduce this initiative to those who don't know this project. So, Marcelo talk a little bit about my trajectory. I'm currently a faculty member of UFRJ, Universidade Federal of Rio de Janeiro. I am a chemical engineer, as Marcelo told, and did my master and PhD studies under his supervision. At that time, we went from model simulation control of running circuits. We did like more than 20 years ago, and then we moved to develop mechanistic modeling of comminution processes, starting with the ball mills and then jump into SAG and NAG mills in my PhD. So among the research topics that I work with, so it's model and simulation of comminution circuits, the mechanistic modeling of comminution processes, DM applications such as advanced, what they call advanced simulation of materials handling, that we couple material handling with some breakage models to predict the material degradation for many other industries, not only on mining. Here are some examples of that. So the topic of this talk is comminution circuits, model simulation. So I bring you here some challenges that we face when dealing with comminution circuits. Usually we have fluctuations or disturbance in the process that may come in the feed. Here are some examples of how some beam levels fluctuate along the time. The feed rates that may be changed manually by the operator, or can be changed by the means of automatic and supervisory control. and how that affects here the product rate, the production rate of a certain unit in a circuit. So with this type of fluctuation, we have constant change in the circulating loads of the circuit, mainly because the circuits are almost all of them are almost closed circuit. We have issues regarding limitation of sensors. We can't detect everything when dealing with solid strings. So of course there are new technologies emerging, but we don't have as the availability that we see on other industries, for instance, on the oil industry, controlling gas flows and fluid flows. We face lots of non-linearities in the process, like changes in transformation rates when the ore changes its grindability, that will change, affect the breakage rates inside ball mills. You have change in material density that affects the classification stages, all sorts of issues related to the nature of the ore that will cause and result in non-linearities in the processes. And of course, regarding material transport, the material streams, the material has to be transported from one unit to the other. So the accumulation of transportation delays adds non-linearities to the process. So it makes it difficult to model this type of circuits. And of course, the integration among different unit types. So all the units in the circuit are connected, and the units downstreams are affected by the results or the outcomes of the units upstreams. And we are also dealing with multi-component strings. So sometimes we need to deal with mixture of ores, or even within the same ore, we see different what you call components that will present differential breakage. So the harder material may lead to increase in the grindability, and also the result in differential separation. So the material that is coming back to the comminution stage is not the same as the one that you are feeding into the system. So we have to deal with that as well. Of course, the liberation, we want to grind for the recovery, we need to in the metal, and need to break the rocks. And this is also challenging, not only in the practice, but also more modeling the liberation. And of course, we're integrating machines along the circuit, and there are some new equipments and processes being developed, and they need to be integrated. You need to evaluate their response when placed inside the circuit. So, and there's no, for some of those new machines and processes, there's no mathematical modeling or model available. So we need to develop those models. So there's also a challenge that you have. How can you predict performance of the circuit for these new machines when there is no model available for them? So where do we want to be in terms of a modern simulation? We want to be able to simulate operation from run of mine, feeding the circuit. So from run of mine crushing down to the solid liquid separation. This is what we want to be, what we need to reproduce, mimic the real application. So for that, we need a multi-component structure. So we need to be able to deal with our types, all types of ore and adiposity, in terms of neurological and liberation components. So not only dealing with differential breakage, we need to also to predict, be able to predict how these materials are being liberated and how they will perform in the circuit downstream. So we also need to be able to simulate circuits with different time scales. So we need models to be able to simulate the short-term effects, so we can evaluate and design and control systems and evaluate control strategies for it. Can be specific to a single unit or also for some units or a bunch of them in the system. And also we need to be able to simulate the long-term process, so we can provide like metallurgical predictions and predict circuit bottlenecks and do life of mine studies. And also in the long-term predictions, of course, predict some effects like wear, like liner wear, grinding media wear, idle cyclone wear. So it's not a short-term prediction, but we can also call a term like when we simulate like months of operation. And we need to have an integrated structure to deal with our preparation, concentration, solid liquid separation. So this within the same simulator structure, we need to be able to deal with all those types of process. And of course, with that, we need to be able to analyze the effect of process disturbances, such as like fluctuations in feeds, fresh feeds, just like the picture that I showed in the previous slide, to design and tune control systems. So regarding simulation, one tool that we have been familiar for many years is the steady state process simulators. So basically in this type of tool, we have units or process models that are connected and can interact with each other. They can be organized sequentially. So we have like one feed coming from here, so there is a unit, and then the unit 1 passes the output to unit 2, and so on. So they can be solved sequentially. So basically, if you know the process inputs, the characteristics of the input string, and know the parameters of the units model 1 here, you can calculate the output of these units and so on. Or you can have the units and process model organized with recycle strings, just as this picture here on the top right. So unit 1 passes its output to unit 2, then to 3, and then you have a final product here, the X4 string, but unit 3 also returns this string X3 here to unit 1. So this is a recycle. So you can solve this type of diagram here, unit diagram, using some equation-oriented solver, which is basically collect all equations regarding that are describing this process here, identify the unknown variables, and then you organize that in order to find this unknown variable set. Or you can use solving modularly. So you solve using a unit-oriented solver. So you solve sequentially, but when you face a recycle string, you have somehow to use an algorithm to open the circuits, like guessing one of the strings here, which is called the tier string. And then if you guess, for example, when you're solving for the first time, you can guess like the values of X3. With the known X1, you can solve all units here sequentially and then have a new guess. So the algorithm here is iterative. And the idea here is to have a process simulator of model that mimics the behavior of the real system. So when the systems can be complex as this one depicted here. in the diagram on the top, on the bottom right. So when you call steady state simulators, we are just solving this set of algebraic, linear, and nonlinear equations. So basically, all model equations have this time derivative as 0. So there's no variable varies with time, and we're describing like models with inputs and outputs. If you take, for example, the perfect mixing ball mill, which is a well-known model, you have the input feed rate here, W win. The mill has hold up, the amount of ore inside the mill, represented here in the box, and the output here is W out, that you can use like a power relationship to guess, so to calculate this feed rate of the mill, the rate of the mill, using the mill hold up as a parameter. If you take like the population balance equation, considering the transient state, we have like the derivative of the amount of material that's within the size class I and the component class K with time. When you have here the mass rate of material of the class I entering the mill minus the mass rate of the material of the class I exiting the mill, we have the disappearance term due to breakage of those material within the class I, and the appearance of material in the class I given by this term here. So in steady state, this whole term here turns into 0. And with that, we can say that the feed rate is equal to the exit rate or discharge rate, which is we call here W. In this differential, this system of differential equation, because we have a differential equation like that for each size and component class, becomes a algebraic equation that you need, in order to solve it, you need to know the feed size distribution, the mill hold up M, and the discharge or feed rate W, because there's no variation in hold up anymore. So this is the steady state solution. And the thing is, when you performing dynamic simulation or organize some flow sheets in order to perform a dynamic simulation, for some units in the comminution circuits, you can assume that they will give an instant response, and you may say that it varies with time when you consider just that the inputs to a steady state equation are changing. So basically, we have an instant response of that machine. This is usually can be considered true when we simulate like fast machines when compared to some others. For instance, in a mill, you can have like residence times as high as half an hour or even more, while in crushers, the material takes just a few seconds to pass through the crusher. And for example, for crushers, you use like equations like that in the steady state inside some dynamic simulation scheme that will, when combined to dynamics coming from like silos, hoppers, and beams, and conveyor belts, they perform as a dynamic circuit. So that type of model we call like the pseudo-dynamic units. So they are fast process compared to the process time scale. It's just a set of algebraic equations that, of course, there can be some differential equations, but we are not solving these equations with time. So we can say that crushers perform like that, like hydrocyclones have fast dynamics that when simulating a circuit scheme, they can be considered as instant process. In the case of screens, that may be some dynamic here. Some approaches consider screens with a residence time, so they can retain material for a bit longer time, but they also can be modeled as FS, even just, for example, like as just a single partition curve using the well-known Carras or some type of Carras model. And you have the natural dynamic units. In this case, just as the bomb example that I showed you before, you have transient mass balance equations. So the derivative of state variable with time is not zero anymore. So you have to consider that and integrate that using like one solver, an integrator to solve the system. So we can mills with transport equations, they are materials machines with natural dynamics. So if you, like, for example, change the feed rate, this increase or decrease in the feed rate will propagate and be transferred inside the mill, and it will take time to see the full mill response. And the thing is that when you perform a steady state simulation, this transient behavior, when you perform a change in the process, will not be seen. Sometimes that there's a risk that you miss when you jump from one state to the other, that you miss some bottlenecks, like an overshoot, the mill may become clogged or overfilled for a certain period of time that you wouldn't see and when doing steady state simulator. So when there's this transition between steady states may show you some bottlenecks that you can only see or predict using dynamic simulators or simulations. In the case of SUMP, is a natural dynamic unit because you have the material being mixed there. They need to be pumped to the hydrocyclones. There's usually this operation. You find like control systems to keep the level, or you can keep like the solids concentration. So you have to have a dynamic model there in order to describe well the SUMP units in the circuit. And of course, silos, beams, hoppers, stockpiles, all this type of units, they accumulate materials. Some of them performs a degree of mixture of materials. So if you have like one type of material, like let's say weaker material feeding a silo or a hopper, depending on the configuration, if you like start to feeding like a harder material, this harder material may exit the silo or the beam with a degree of mixture with the weaker material. So you have to model that, and so we have some equations, but mass balance equations to describe. So there are some approaches here. You can model like a series of mixtures or a series of parallel reactors, mixture reactors. But the goal here is to avoid like that the simulator is saying that when you feed a silo instantly, the material discharge from the silo is equal to what is being fed to the silo. And of course, the screens, as I said, they can be modeled as by dynamic units as well. So regarding the dynamic simulations, of course, you have to do variability. In summary here, the feed properties of the material, variability in the equipment wear, so they may lose performance a long time, and changing with the operational conditions. Sometimes the change in the operational conditions comes from the operator. They see the circuit performance for a certain way, and then they change some of the parameters. We need to be able to predict and simulate the impact of when an operator change some parameter in the circuit. Regarding equipment performance, as I said, there are some approaches that our group from GCC group has tackled. Like the guys from Chalmers, they be modeling like beam sump silos and flow controllers. And regarding mills, we done simulations and modeling considering load dynamics, restless time, transformation between the mills. In this case, the breakage may vary with the hold up. And this is the type of result that you get from a dynamic simulation from a single unit, a single mill unit. So a long time here, you have the mill hold up, the blue curve here, you decrease the mill hold up, and then you see the response in the mill discharge rate. This is after we decrease the feed rate of this mill. So basically, the pretty nice curve, first order curves here. Of course, when you simulate in the evolution of size distribution, they're not as well behaved as that, but just to give you an example of outcome from a dynamic simulation. So, so now I want to show you some case studies that we performed within our group. So the first one is a long-term simulation of a rod mill circuit. It's not in the mineral processing, but it's an interesting circuit, an open circuit. In that case, we are evaluating what measure we could take to deal with the grinding media wear. So the rods would wear on time, and we wanted to extend the life of these rods while keeping the quality of the product. The second case is a simulation of closed grinding circuit of iron ore using the features of the Dyssol simulator that I'll talk at the end of this presentation. In terms of components tracking and how the dynamic breakage rates, so change the mill conditions and the composition of the hold up, how this rates will change when you're dealing with multi-component ores. So the first case, which is the rod mill circuit, here's the mill. It's 2.5 by 4.3 meter rod mill. It is used in the preparation of coke for a sintering plant. This imposes a limitation of operation because the sintering plant has to receive a constant feed rate. So the circuit's here, so it's open circuit. So there's a screen at the beginning. So the oversized materials feeds the rod mill that's transported by a conveyor belt to another conveyor belt that feeds the silo. And this silo acts as a reservoir of material to feed the constant feed rate to the sintering plant. So the rod's diameter here starts as 75 millimeters. So the operators, they start with the brand new rods with an initial filling of 15%. So a long time, due to the wear of the rods, the mill filling reduces. And they operate in the certain way that they wait for the rods filling due to wear reach almost 4%. So they stop the mill and change the rods, placing a new charge inside. But the thing is that the material is subject to moisture, and that degrades the performance of the screen. So where the screen becomes clogged when the moisture degree is above 30% in the material. You can see here in the partition curves for the screen. So when the screen while it's clean with no moisture effect, the partition curve shows as well a nice curve here with almost zero short circuit, just a little bit of fish hook effect here. And then when time passes, the screen loses its capability of separating the material. So there's a lot of short circuit here. So the mill is fed with finer material. So the things that we need to keep a constant rate here to the sintering plant. So here is what we obtained by simulation. So for that, we consider the population balance approach to model the rod mill, consider plug flow. So basically the material is being ground as a batch, in a batch process. The duration of the batch process is the residence time of the material inside the mill. The screen is modeled as an instant process, so just a partition curve that can change with time. So the dynamic aspect is placed on a model that correlates the screen performance with time and moisture that can fluctuate. The conveyor belt considers the time delay, the transport delay, and the silos are modeled as a series of mixers. So for the base case, we have just reproducing what the operator did there. The operator decreased the feed rate after a certain number of days. So you can see here, after 20 days of operation, there is a step change in the circuit feed, and then with that, the mill feed, which takes the oversize of the screen, decrease as well. So we found 1, 2, 3 step change to the feed. So the capacity of the circuit reduce. And then you can see here the predictions of the mill filling due to the rod wear. It goes up to 90 days of operation. And due to this is the long-term simulation, but due to the screen cleaning and there are some short-term simulations, the short-term dynamics that we need to look at. For example, here, if you take a time window from 205 and 215, there is this change in the mill feed due to the screen cleaning. So it starts well here with the cleaned screen, and then it saturates to higher mill feed due to the screen become clogged. So that the material fed to the mill is fine. It feeds more fine to them. So some results here. So testing some alternatives for dynamic simulations. So we tried some approach like continuously reducing the feed rate instead of performing step change just like the operator did at that time. We have this red curve here showing the constant change, or let's say lots of small step changes to the mill feed, or we try to keep the mill power constant by changing the critical speed. So with the filling, mill filling going down, we continuously increase the mill speed in order to keep the power, as you can see here on the top right graph here. There's some strategies keeping the mill power. Of course, the simulation is a nice toy because we can evaluate all those scenarios, and we've been able to extend the lifetime of the rods, like from 90 days up to more than 120 days, by keeping the product quality as most as constant. But this was a nice case that I'd like to show you. The second case is the simulation of closed grading circuit of iron ore. As circuits dealing with iron ore, especially in Brazil, they have to deal with feed variability. So there's a continuous decrease of ore quality, the grade, and the increase of our competence. Now there's this push for processing iron ore from tailings, and also this operation of mixing different ore types. So we're mixing materials with different breakage characteristics and competences and work index. So we need to somehow be able to check how this material behaves. So you can see here some different materials with different colors representing this different type of ores. So usually this is performed by using simulations based on average parameters, but now we want to go further using this nice feature that Dyssol has, which is dealing with multi-component material strings. So what we idealized here, considering the representative material of the Brazilian iron ore, which is mostly hematite and quartz, consider different properties. So the density has come from 2.6 of quartz particles up to 5.1 tons per cubic meters, representing the hematite particles. Each of these components have its own grindability, and the ore have its own composition. So the combination of hematite, quartz, fully liberated particles, and also some mixed particles that we call here the medians. So we wanted to evaluate the potential buildup of the components with the higher competence in the mill. Really perform the simulation of this closed circuit operation, considering the possibility of selective grinding. So each component has its own selection function, its own breakage rates, and also the classifier operating based on the density. So for that, we then define the multi-component iron ore composed of hematite, quartz, and middling, which represents the non-liberated particles. We just grouped those non-liberated particles in a single component here. So we define two ores. The iron ore 1 here, IO1, which is richer in iron, and iron ore 2, which presents as finer size distribution. So you can see here the finer size, the size distribution of these two ores. So and then how we structured that in the simulator. So you set up a flow sheet receiving these two ore types, and if each ore type representing a certain percentage of the feed. So if you take like the iron ore 2 here, it's composed of 37% of hematite, liberated hematite, 15% of the mixed particles, and 48% of quartz particles. So this is defined as iron ore 2. So this ore type here receives a tag, so it's a property, it's called a tag, and then it's receives its size distribution. And each component here has its own breakage function parameters. So when particles break, they will produce a progeny that follows the traditional breakage function. It depends on the parameters here, and also it has its own selection function parameters that I'll show in a few slides. So the circuit that we're talking about, we chosen the idealized circuit here. So ideally, we would have to simulate like the addition of water and the mixture here in the sun, the dilution in the sun. But for simplification, just considering the comminution and the classification stage of the circuit. So if considering like a representative ball mill and for an overflow discharge. So we perform these simplifications, and the hydrocyclone, we are not considering the dynamics within the hydrocyclone. It's just modeled as a partition curve that is selective to density. So for the ball mill, we consider the perfect mixing model with a transport equation. So the hold up of the mill can change along time. Like if you overfeed the mill, the hold up will increase, and with that, the breakage rate will decrease. So the product will become coarser, and also not only if you don't consider that in the model, if you increase the hold up, the residence time would increase, so you would get like a final product. But we need to consider that the mill is overfilling if you increase the feed rate, and that will reduce the the breakage rate of the particles due to cushioning of the wall impacts. And as I said, the hydrocyclone will be modeled as a partition curve as function of component density. So for the mill transport model, you're using like a mass balance here. So it's basically the rate of variation of the mill hold up is the feed rate minus the discharge rate here given by this power relationship of the hold up. So basically we need to integrate this differential equation here to get the mill hold up, and the population balance equations are used to model the evolution of the size distribution of the material in terms not only of the size, but also in terms of the component K here. So you're solving this system of differential equations for each of the components, the hematite, the mixed particles, and the quartz particles here. So just to give you an idea of how different the materials are, we have this specific breakage rate, which is selective of the material. So, for example, for the hematite particles, the blue curve here in the left graph, for particles coarser than 1 millimeter, they have the highest breakage rate, while the quartz particles are tougher to break. But for finer particles, the quartz are easier to break here, so they present a higher specific breakage rate. Regarding the breakage function of these materials, the quartz produce, when they break, they produce a coarser distribution, while the hematite and middlings produce finer distributions. This data is based on real Brazilian iron ore. And for the classification, this is how we model. We consider the selective to density partition curve. So the cut size here for the hematite is the blue curve here. It's finer than the cut size for the quartz particles, the orange here. We found that using classic values from the literature. So when we perform the simulation, just looking at the steady state results for the mill, the circuit goes through a transient stage until it reaches the steady state. So consider a feed of 70% of iron ore 1 and 30% of iron ore 2. Almost 210 tons per hour fresh feed. We saw that the recycle stream here, the green circle, became richer in the hematite because they are being rejected more in the classification stage. So the recycle stream is also richer. You can say that it's also richer in the iron ore 2 material and richer in iron as well. And the mill discharge, that state, by combining all the strings, it shows an average grade of iron. And we have also the composition of the mill hold up as function of the size class. So you see that in the mill hold up, they are richer in the iron ore 1, which is richer in iron for the finer size class here. So moving from the steady state result to the dynamic results, we just to play with the model, we introduced the step change at the 108-minute mark. We changed the composition of the feed. So moving from 70% of iron ore 1 to 45% of iron ore 2. So you can see here the step change. So we starting feed to feed the poorer iron ore here. We see a change because we changed the amount of material that presents differential breakage rates, we see a change in the recycle string, showing this pretty nice first order curve here, because now there's less hematite in the circuit. And looking at the individual components dynamics within the circuit, first at the input string. So when you change the composition of the feed, of course, changes as well the components distribution in the string. So that there is now more quartz entering the mill, liberated quartz entering the mill, less liberated hematite. And in the recycle string, now the green curve here shows the decrease in the hematite composition in the recycle. Now there's more quartz in the recycle string. And the mill output as well, we see that there's this decrease in the hematite composition, and this can be considered a long time dynamics, because if you see here, it takes more than 1 hour for the system to reach a new steady state. So in 1 hour, if we are just performing steady state simulations, we are missing this transient stage here that change the composition of the mill output. So the composition of the iron ores in the recycle string jumps from 73% of iron ore 1, and after the step change to 49% of iron ore 1. Okay, that being said, I just want to take these last minutes of my presentation to talk a bit about the GCC Dyssol Pro initiative, which is the multi-component dynamic simulator. So the idea is to have this single platform among the GCC group and partners, so the GCC research centers and institutes can develop their models and implement that and in a single integrated platform. So Dyssol is the acronym for the Dynamic Flowsheet Simulation of Solid Process. It was the first developer of the Hamburg University of Technology. The first prototype was released in 2014. It's written in C++ language. It has connectivity to other high-level languages such as MATLAB and Python. We, as GCC group, we elected that as the dynamic simulation platform of the group. In more recently, there is the development of this new advanced version of the Dyssol, which is called the Dyssol Pro, between this spin-off company Dyssol Tech. And we took the last couple of years to validate this Dyssol, the Dyssol as dynamic simulator tool, against other tool for crushing and ball mill circuits. On the right here, you can see a comparison between the Dyssol results for like crush plant operation and also for a mill operation when compared to a traditional approach using MATLAB Simulink. And this year, the Dyssol Tech released a new version of Dyssol Pro. So as we choose this dynamic simulator platform to be used within the GCC group, we developed this dedicated version of the simulation, which is called the GCC Dyssol Pro, and we implement the models developed and used by the group. So we have the quality insurance of the models that are implemented and will be implemented there. And we perform the validations, as I said. So basically, we have this structure here with a graphical user interface for input and output of the data, a couple to process control features. We have all the models that we work with and we develop implemented in this Dyssol platform. why we choose the Dyssol? Because it's a robust multi-component framework. So remember that I said earlier that we want to be able to simulate from the run of mine down to the separation stage. So with the integration of the stream product along the entire combination circuit. So if after you define the material properties, it will be carried over the circuit, regardless if it's a crusher or a mill or a separator or a classifying stage. So properties such as a particle size and shape, the density that was just like in the example that I showed in this presentation, like charge, gradient, all of the properties that you can think of regarding ores. There's this ease of model implementation. We can fast prototype models in this platform. Regarding the simulation, it solves in a modular approach, so it defines, it uses the waveform transforms to implicitly integrate the circuits a long time. So it divides the circuit in subsystems that can be parallelized and perform fast calculations of circuits. And it can deal with multiple recycle streams. That's important because we sometimes find circuits that's in a complex configuration with many recycles, and then couple that to dynamic simulation is not that simple to obtain a reliable solution. So regarding the interface, the current version of the Dyssol Pro has this nice flowsheet design and with some library of models. Of course, in the GCC, we will add the relevant and standardized model icons here regarding mineral processing, because the original Dyssol was developed for chemical industry using solids, but we want to translate that into the mineral processing units. Just an example, for the case that I showed you with components track, this is how we define the material. Regarding the components here, the hematite mix and quartz, the ore type, 1 and 2, the tag here, and the size distribution. So it's a simple structure like that we can do with several levels of material properties that can be integrated in the stream characteristics. So, so with that, I'd like to, for those companies that are not yet part of the project, we would like to invite you to join this initiative. So we are distributing the material. So if you want to know more, just contact the GCC through Tulio. And with that, I conclude my presentation. So, but before that, I'd like to thank Dyssol Tech for leaving this partnership, and also my master students, the Rodrigo Carvalho, which is the guy behind the simulations and the Dyssol model implementations that I presented here in this talk. So thank you.
Thank you, Rodrigo, for the presentation. So we have time for a couple of questions here. Just raise your hand or open the mic and ask the question. Olga.
Yeah, Rodrigo, first of all, thank you very much for this very illustrative presentation. How do you see the opportunities? I mean, you elaborated quite a bit on comminution issues and screening, a little bit on density separation also already, or density impact. How do you see the opportunities to link all that flow sheet simulations, that dynamic simulation, to things like magnetic separation or the flotation? I mean, at the very end, the target of mining company, typically, or processing company, is to produce a concentrate, and you have, of course, a lot of impact. We've seen this nice density distribution or particle size distribution and quality changes, and this density distribution has an impact, for instance, on the magnetic separation if you go for magnetic separation. So the finer particles are more difficult to capture on the one side. On the other side, if they have a higher susceptibility, that might influence the operation in different directions, and that is typically quite difficult to capture.
Yeah, I think it's doable because we can take advantage of the material string structure that Dyssol provides. We can add the components properties such as magnetic susceptibility. It's just a matter of having the model responding to that property, because it will be carried over the circuit down to the separation stage. So when the feed string reaches that point, if the magnetic separator model is responsive to like magnetic susceptibility, the magnetic response of the component, it can be modeled. The challenge of that is to have a good liberation model within the comminution stage, and this is something that we are trying to improve. Like we have this like Marco Hilden's liberation model to be used as a platform to develop good models. This is a thing that GCC researchers are working on. So I think it's doable, and it takes advantage of having the Dyssol platform as a tool that's already has the structure to deal with these different properties. It's just a matter of how you describe that, but it's doable, and I think we will reach that point.
Okay, thank you.
Because we have the structure. It's just a matter of having the accurate separator model.
Okay, thank you.
We have maybe time for another short question. Anyone here in the audience?
I might ask a question. Thanks, Rodrigo. So something I guess you didn't manage to get to is that the process control system on top of the dynamics. So it's very clearly my experience that if you can go through a transient state you can't recover from. So you can't get to what a steady state will predict quite strongly in sag mills, but you can go transient through an overload and you're done. And just maybe you could express what could be the value of simulation, understanding that those issues around the transients.
Yeah, I proposed it let's control off this presentation, but of course I recognize it's important, of course, but having the dynamic simulator, without that you wouldn't have a tool to design and tune the control systems. But the first stage you have this dynamic simulation. But I think the process control is a whole another topic. Like it may take like 40 minutes just to talk about that. But of course, some process they don't they can't be like they run without control, because we're operating near the pinch point, which is the abyss. If you don't want to, we need to be close to the abyss. But if you go a step further, we'll fall down and everything will lose, just like you said in the sag mill operation. But you can also not in a critical, it's in a sag, but like in ball mills, you can mess with the operation as well if you don't have control. Like if you mess with the solids concentration, for coming from the recycle, or if you don't feed don't control that, you lose your operation. But some type of control we do, like I think the operators they perform manually with just looking at the circuit sensors, the supervisory system that they have. But the automatic control for that development, we need to have the simulator. So I think one thing can't be decoupled from another. But there's a whole new another topic for discussion that perhaps in the future we can tackle. But of course, when I talk about the GCC Dyssol Pro initiative, we have the control tools there. One of the validation case that we performed last year was controlling a crusher plant with like silo levels and beam levels. Without that, a crusher plant wouldn't operate as well. So we need to shut off some feeders in order to avoid overfilling in silo or reaching the maximum capacity of stockpiles. If that you wouldn't be able to do like using just like a steady state simulator. This is the message that I have. Yeah.
All right. So thank you, Rodrigo, for the interesting presentation again, and thank you all for attending this seminar today. So next month we have another one, and we will receive the invite soon. Thank you very much for joining.
Thank you.
Bye, everyone.
Thanks, Rodrigo.
Bye.
Cheers, everyone.
Thank you very much.
Thanks, Rodrigo.
Everyone.
Bye, friends.
Bye.